Hey folks, in this video we are talking about heating curves and also cooling curves. So we got a few objectives. I would like you, dear viewer, to be able to create or analyze a heating curve. Create it if you're given the data, or analyze and pull some data out of one. I'd like you to be able to perform calculations relevant to heating curves and also cooling curves. And let's get rolling. Heating curves, what are they? Well, they're graphs that show how temperature changes with time during phase changes. So we've got a substance we're studying, it goes through some phase changes. This graph will show us how the temperature of it changes over time. The x-axis on this dude is going to show us time because that's pretty much always where you put time. And the y-axis is going to show us the temperature because we're looking at how that changes over time. So here we can see it. We've got temperature on our y-axis and time on our beautiful x-axis. And we can see temperature's going up, stays constant, goes up, stays constant, goes up. All right, what's going on there? Well, let's talk about it a little bit. Temperature stays constant during a phase change. We talked about that in the phase changes video. You know, if you have some ice water and that ice is slowly melting, if it's perfectly mixed up, the whole thing should be right at that freezing point, 0 degrees Celsius, which is a nice, pleasant temperature, although a little cold on my teeth sometimes. Or if you've got some water boiling, that whole water is going to be at 100 degrees Celsius until it all boils off. And if you have any trapped steam, that steam should stay at 100 degrees Celsius until it is all the water has boiled into steam. Neat. So that tells us that these flat portions of the line, where we have a constant temperature, that's where things are either melting or freezing or boiling. And at this point, we're going to have a mixture of our two different states. Well, why don't you pause the video for a second and see if you can figure out what's going on during these different stages right here, between A and B, and between B and C, between C and D, etc. Pause the video, give that a shoot. All right, sick. Let's talk about it together. Well, during A and B, we can see the temperature is going up. It's warming. Between B and C, we can see the temperature is constant. So that means we've got a phase change going on. Between C and D, we can see it's warming up some more, and then we've got another phase change going on here, and then the temperature warms up between E and F. Let me pause the video again and think, what phase changes are going on here and here? Pause it. Think about it. All right, well, you've done thought about it. So between B and C, we've got a phase change here, and then another phase change at a higher temperature. So this is most likely then going to be it melting. It's gotten hotter, and then a phase change occurred, and then another phase change occurred. If we have another phase change, that's probably going to be boiling. So that means that this is a solid getting warmer. This is it melting. This is then the liquid getting warmer. And then this is that liquid boiling. And then finally, we have that gas getting warmer and warmer. Get out of there, wine grad face. It's getting warmer and warmer. That gas is getting warmer. Okay, cool beans. Go back, wine grad face. So let's talk about how we're going to use this to do calculations. Ooh, they get a little spicy. Watch out now. So we know we are able to calculate the energy that's absorbed or released during a series of phase changes. And we can do this by drawing ourselves a heating curve and determining what equation we're going to use to calculate the heat absorbed or released during each segment of the curve. Whoa, whoa. And so if we calculate the energy that's associated with each segment of our curve, then we can add all those up and get the total energy. So let's try a problem out. Let's try a problem out right now. We got 780 grams of ice at negative 20 degrees Celsius. It becomes steam. It's heated until it becomes steam at 120 degrees Celsius. Let's use this guy as our heating curve for this. And we want to figure this out. Well, between A and B, we know that ice is warming up. So we can use our Q equals MCAT equation to figure out, with the temperature change, what's the energy? It's the heat absorbed or released. And we're going to need to use the specific heat for ice. If this is water, or H2O, it's starting off as ice, which has its own specific heat. And then in between B and C, we're going to use our phase change guy. We're going to use our enthalpy of fusion because that tells us the heat that's either absorbed or released when something melts. So if this guy is becoming a liquid, it's probably absorbing that heat because it's got to get faster and faster, those particles. And then between C and D, we know we're going to use Q equals MCAT again because it's getting warmer. Anytime we have an increase in temperature or decrease, that's where I'm going to use Q equals MCAT. When the slope is flat, that means we have phase change. So here we said we're going to be boiling or vaporizing. So we'll use our enthalpy of vaporization to calculate the energy associated with this segment. And then, oh my goodness, we're going to use Q equals MCAT again, now with a specific heat of steam, not ice, not water, but steam, and we'll figure out the energy associated with this final change. Let's do a slightly different problem though. Why don't you, after we talked through that, pause the video and see if you can do this guy. See if you can draw yourself a heating curve, and then see if you can come up with the total temperature, or rather heat that's absorbed or released. Pause the video, try them out. All right, sweet. Let's go through it together. So first thing I want to do here is draw myself a heating curve. We've got water. It starts at 50 degrees Celsius and goes to steam at 125. Oh, and it's going to boil at 100 degrees Celsius. All right, so I'm going to start off my graph. Let's put on some axes. All right, I'm going to start at 50 degrees Celsius. I know it's going to go up to 125. But at 100 degrees Celsius, that's where I'll have my flat portion, my phase change. All right, so it goes up, it gets boiled off, and then it gets hotter again. Neat. And I'll just label these segments for convenience. And yeah, so I know during A and B that water is warming up. I know between B and C it's boiling. And then I know during C and D it's warming up again. So I know which equations to use because when it's warming, I use Q equals mc delta T. And when a phase change, I'll use Q equals the enthalpy of vaporization or fusion times the mass. Or moles, but all these guys are in grams. So that's convenient. We can use our 75 grams and not have to do any unit conversions for moles to grams. Well, let's go ahead and plug all this stuff in because I think we got all this stuff. During this first segment, it's important to remember we're only going from 50 to 100 degrees Celsius. So our final temperature is 100 and we started at 50, but we can plug all this stuff in and solve for this first Q A to B. I like labeling things. It's nice. So we know that's that temperature or that amount of energy that's going to be absorbed to heat it up. And then we can go ahead and figure out how much energy is absorbed for this phase change. All right, well, we know the enthalpy of vaporization, and we know the mass, so we'll multiply them together to cancel out those grams and give us the joules. Sweet stuff. And so that's going to be an easy calculation. That's a lot of energy. Jeez, it takes a lot of energy to vaporize water, I tell you what. And then we can figure out the energy associated with heating up that steam. So now we have to make sure that we use the specific heat of steam, which is less than the specific heat of liquid water. But we can plug all this stuff in. We know the final temperature of 125, and we know it started off at 100, that vapor. Cool. So we'll plug all this ish in, and we'll get our final Q, and then we're gonna add all those suckers up and come up with a total heat of 188,800 joules. Rounded. I rounded. I took some liberties. So this is not too spicy, but it's a lot of small calculations that need to be done. Anyway, that's the end of this video. I hope you understand what a phase heating curve or cooling curve. We didn't look at any cooling curves in this video, but they just show stuff getting cooler. It's the opposite of a heating curve. But I hope you understand what they are. I hope you feel like you could draw one if you're given some information and do some calculations as well. Ta-ta! Have a great rest of your life.